Well, welcome back to our discussion on being able to calculate area between curves. Previously, we had seen this idea. So given one function, let's say we call it f of x, and another function here, let's say we call it g of x, and given an interval, a stated interval, can you determine, no matter what that shape, the value for area between those two curves? So whether these two curves are above the x-axis or below the x-axis, our answer will always be a positive value. So this is as in determining surface area. As long as you knew f of x was greater than g of x on this entire interval, you would always get a positive answer. In the case where maybe you were given two equations, but you didn't have a graph to support your work, you weren't sure which equation was necessarily the higher equation, then we had the use of absolute value signs. But we ended up with the formula stating that to figure area between two curves, it came from an integral on the interval that we were given, and we would just calculate the value of function f minus function g, and that would give us our value. In a case sometimes where they didn't give you this interval, then it must be an unspoken or an implicit situation where the graphs are crossing. So perhaps I have a situation like I've got a trig graph and I've got a parabola. So they might not have told me where did these graphs cross. I would have to figure that out first for myself. So the idea, what area is bounded by these two curves, where they would intersect. So I would take this function and this function, first put them equal to each other to find out those points of intersection. So that would be the first consideration. But then I would know the a and the b value. A graph is so helpful because right now I can see the trig graph is the lower of the two functions compared to this parabola. So for me to be setting up my integration, now that I found these values of a and b, I would state the parabola first. So this upside down parabola would come here first. From that, I would minus my trig graph, and that's how I would find the proper value. If I didn't have that graph though, I could save myself by simply, after I've done the integration here, putting absolute value signs around me because of the possibility maybe I have these backwards. Maybe this isn't higher minus lower. Maybe I've got it switched around. And we also could use our definite integral key, our Math 9 key, to enter all this. So after you've entered your limits, that's when you would press absolute value sign and type in your equations. So we had that situation. Then we had one more situation. What if the graphs cross more than once? So what happens now is the graph that at one point was the higher graph is now the lower graph. So a situation, again, maybe I have a trig graph here, and then I have a line. So for part of this situation, and I'm supposed to be integrating from, let's say, from their first intersection to their last intersection. So for this brief time period, it would be the trig graph that was the higher graph. But after that, then I see it is the linear graph that is the higher graph. So this had to be broken down into different intervals. I need one more spot right here. So this is if I'm actually doing my work by hand. If I'm just using a Math 9 key on a calculator, the calculator will take care of everything for you as long as you insert absolute value signs. But to show my work mathematically, I would first have to put these two equations equal to each other, find out this meeting point right here, and then break things down. Say, okay, so I'm just going to call this C. From A to C, I have the trig graph minus the linear graph, but from C to B, I would have the linear graph minus the trig graph and do it that way. Or if I still didn't have the graph to support which one was higher or lower, after I had those two integrations, just have them each separately in absolute value signs. So the more times they meet, the more work for you. But you do have that Math 9 key, but you have to know how to be entering everything properly. So from there, then we had the idea of symmetry. Sometimes, because this is about being able to do things algebraically, if you can do them with less work, why wouldn't you? So let's have a look here. How about if I have a sine graph? Okay, so here's my sine graph from 0 to 2 pi. Just to simply use a Math 9 key, I'm going to get the value for the area between the curve and the x-axis to be 0, because this is a positive value. This would be a negative value. They are identical, so my answer would be 0. We know that's not right. We're looking for true blue space being occupied. So there's a couple of ways around this. If I want to do this, then simply using a Math 9 key, I could say I'm going from 0 to 2 pi, but I'm going to want everything here turned positive. So I could now say, or enter that into my calculator and figure that out. I will now get, I think it's 4. So otherwise, without these absolute value signs, I get 0. This area is positive 2, this area is negative 2, and that's why it would give me a net area of 0. But actual true blue area covered, I now have a value of 4. We saw before the idea of using symmetry. This area is identical to this area. This stopping point would be pi. So another way of looking at this is saying, you know what, I know this area over here is just a duplicate of this one. I'll just double the integral from 0 to pi. So another way, using symmetry, I could have gotten this proper value is saying, I'm going to double. I'm going to take 2 of, here comes the area, from 0 to pi, and this is sine x dx. Doing this either by hand, so going backwards and figuring out the integration for sine x, I will still end up with a 4. So this idea of symmetry is very, very handy because it will offshoot things that would have been positive and negative. So we saw symmetry before in your previous lesson. So I've got our textbook here. What are smart cases where using this idea of symmetry would alleviate a bunch of your work? A situation like this one right here. Since right of the y-axis and left of the x-axis, these areas are equal, why don't I just do one value? I will integrate from 0 to pi over 3, but double it. This one, we don't see that happening, nor here, but here's another one. So I've got this area being identical to this area, so less work would for sure be integrating from 0 to 2, and then doubling that value. That would be okay here. Those graphs are just wonderful. With one quick look, you can tell whether or not this would be an option for you. Looking through the rest of the ones on this page, no, these are not good options because you don't have that idea of symmetry. So typically we see the symmetry left and right of the y-axis, but it doesn't have to be. So again, as in this example right here, as long as you are certain these areas are the same, you can just take that division. So it didn't have to be left and right of the y-axis. Okay, so we had that. Now, what is maybe another option for us to look at? When we have this idea, okay, of a higher function and a lower function, this function is something y equals some type of value. This function is y equals some type of value. So these are functions written as y in terms of x. So we cared about which function was higher and then determine the x values that we look at. If I just do a little change and look at this differently, and now talk about these functions as one is more to the right than the other one being more to the left, and now look at the difference in this interval as being a vertical distance, I can maybe have less work. So this is about being able to approach a problem from different perspectives so that you're easing up on your work. So the textbook does give a really nice view of your choices. Okay, so here we go. We are used to kind of looking at things this way. We're used to looking at A and B, who's higher, who's lower. A to B, higher, lower. A to B, higher, lower. We can also look at them this way in terms of F is more to the right, G is more to the left. More to the right, more to the left. And then instead wondering what interval am I going to be looking at vertically. The reason this is sometimes more effective is it depends what form the equations were given to you in. If you were given things as y equals, then you're probably going to keep that and integrate with respect to x, like we always have been doing. But sometimes there are situations where you'll be given the formula as x equals, or the idea of how they're set up. It's so obvious what is more to the right than more to the left. a question like this, for me to integrate vertically and really look at things, I have to split this into two regions. I have to look at the higher function versus the lower here, and then this changed. Now this was the higher function and this line was the lower function. So I definitely am stuck now with two integrations to do. But if I could look at this function as there was a function to the right, and this particular line will always be to the right of this sideways parabola, then I can break everything down into only one interval. So diagrams are awesome, or if you're given the direction to integrate with respect to y instead of x, then you would need to know the procedure we're going to look at today. So it's a new idea. So we've got here, instead of two functions this way, I'm now looking at two functions this way. The one to the right would be f at y. So this function is dependent on my height. This would be my g at y. I would have some start point here, let's call it c, some higher value here, let's call it d. So now I'm looking for this area. As long as I always keep this one minus this one, so my higher, these would be higher x values, minus these values, I'll be okay with my setup. If I don't know, I'll use absolute value signs. I can still use my Math 9 key, and I can still use symmetry as well. So everything we did before, we can apply now. It's just that heads up of what is going to be less work. So what would my formula be now? Well, now I'm going from C to D. It's going to be the one more to the right minus the function or graph more to the left. And notice everything here must have y's in it. So don't worry if you're going to be using your Math 9 key, where you typically would press X, you're still going to be pressing X if you're trying to enter something with Y values. So it's very important, this function right now is the one that is forever more to the right. If you did not have a graph, again, that's where you would put in your absolute value signs to do something on a calculator. If you're going to end up having these two functions starting to cross each other, it probably doesn't pay to try and integrate with respect to y. Just stick with what you were doing before and integrate with respect to x. Okay? But diagrams are very, very important, and knowing where graphs meet should always be your driving force. So, first question, we're only going to do a couple here. So we're always looking for area. So my first example is looking for the area enclosed by x equals y squared and x equals 2 minus y squared. So even the way it's given to you, it's probably a heads up that they're asking you to integrate with respect to y, because these values, I'm not going to say functions because they may not be, but they are expressed in terms of y. But the first thing, no matter what I'm going to do, is figure out where these graphs meet. So let's say you're uncomfortable with this and you decide, no, you actually want to rewrite these so that they are y in terms of x. So if you do a little bit of manipulation on this one, you will get plus or, so I'm isolating y instead of x being isolated. Because visually we're more familiar with these, we're more comfortable with them. So I see a radical graph that is sitting where it normally sits or has been reflected vertically. And if I change this one, there'll be more to it. There'll be a radical graph that's undergone a horizontal reflection, and it's been moved horizontally as well. But the first thing I need to know is I'd love to see the graph, but where do these guys meet? So where does this function meet this function? So it would be, where does root x equals root 2 minus x? So you'll square both sides. You will have this, so we have 2x equals 2, so x equals 1. So these two graphs are meeting at 1. You should be able to picture this one, right? So the positive value would be that graph right there, radical graph. The negative would be the vertical reflection. This one here, again, either subbing in different values, seeing where it's going to be sitting, it's going to go like this. So of course this is off now. All right, so these are my two parabolas. So we're looking for this area. If I'm going to integrate, and I know they meet at 1, so this value right here is a 1. So for me to continue my work, I see there are two intervals, because in this region from 0 to 2, and again it's from graphing this one that I know it went all the way to 2, for this first region, okay, this particular graph, but what is this graph? That particular graph was y equals root x. It was the higher compared to this one. And what was this one? This one was y equals negative root x. So for this integral or interval from 0 to 1, I would have this minus this. But then things change. This is no longer the high graph for this region. Now I have this other one being the high graph. So this function would have been y equals root 2 minus x, and this component would have been negative root 2 minus x. So now for this part, I have a different f minus g. So this is becoming, first of all, a lot of roots, a lot of equations, 2 for sure different integrals. So to get this area, I would be first going from 0 to 1, saying the higher was root x minus the lower. So I would have this one first. To that, I'm going to add going from 1 to 2, and then my higher minus my lower, and and if this is a non-calculator question, you have a lot of work there for yourself. But you would do it, and you'd go through the work, and you get an answer. Really being noticeable, or really being smart here, you might also see these two areas actually would be equal. So you could eliminate some of this work had you noticed the option of using symmetry instead. And you could say, okay, I'm just going to take this area, this function minus this function from 0 to 1, and I'll double it because that would give me the remainder. So that would for sure be a better option than this one. And what would that look like? So this area would be from 0 to 1. I have the top function minus the bottom function. And, but I have to double it. So there's my 2. That will give me the same answer as this. And you can just tell even right now by looking how much less work this one will be than this one will be. So this was a really good option right here. But what if you were meant to keep these as is and integrate with respect to y? The graphs would still be the same. Whatever it's going to take, you would still draw these graphs. But now the meeting point, it wasn't a value of getting this meeting point where you're seeing their x values. Now you need to find out their vertical positions of where they're going to meet. So you would take those equations. So now we have y squared, and so we have these two equations right here. So I'm taking this. Where's it going to equal this? So y squared has to equal this. So we will end up with, by the time we're done here, y is positive and negative 1. So now I have the vertical positions of where they meet. The graph is still the same. We have this, and we have this, and we knew that was 1. But now we have this location being positive 1, and this location being negative 1. And now my eyes aren't on who's higher and who's lower. Now I'm wondering, are one of these two functions simply always to the right of the other one? And you bet, this one right here. For that enclosed region, this graph is forever to the right of this other graph. So this was the graph. This is in terms of x. So this was our x equals 2 minus y squared. And that was this one, and this one over here was our x equals y squared. So this is forever to the right. And that covers the whole region. I don't need to divvy anything up. I mean, I guess I could use symmetry here. I could and say, well, whatever I'm going to get integrating with respect to y from 0 to 1, I can double it. But this isn't that bad work. So now my area would be from the lower interval limit, so negative 1 to positive 1, the graph that was forever to the right, which is this one, minus the other graph. So all of this. Well, compared to this mess that we had over here, this is a much smarter method to take. So I would continue with this one, go through it and get an answer. If you want to finish this off on your own, doing it algebraically, I mean, you'd simplify this first. You'd put together your like terms, do a algebraic integration, and that should be your answer. And don't forget, you can always verify by using your Math 9 key. But this diagram was so useful, and the equations you'll typically be given will be recognizable ones. They shouldn't take you very much time to be able to graph by hand versus, of course, if you have a calculator, you can do it that way. All right, so that's one example there. And we've got one more here. Looking at options, how about if you are looking for area bounded by this, y equals x minus 1, and y squared equals 2x plus 6. So this the way things are written, you're thinking, well, I'm going to keep it this way. I have a line. I'm not sure what I have here. I would have to isolate y. So now we have this. And if I want to fix it up a little bit more so I can see the transformations, I see I have a horizontal compression by half and a horizontal translation 3 to the left, and a vertical and a vertical reflection of a manipulated radical graph. Okay, but these are not that tough to draw. So if I kept everything the way it is and tried to draw these graphs, so here I've got a line, and over here again I've got a graph that went 3 left, so I have something kind of like this happening. So I'm looking for the area enclosed by these two curves. So there it is right there. This graph is awesome to have and look at. So what do I know? This is -3 just by where the graph sits. I would need to know where these two curves meet. So that would be putting this equaling to this and solving. So if I did that, I get, there's a -1 here and there's a 5 here. So is one graph forever higher than another graph? Well, what are all these graphs? This top radical one would be the 2x plus 6. This portion down here would be your negative 2x plus 6. And this graph right here is your x minus 1. Looking at these regions, there's my division. I would have to get this area first. This radical graph minus this one from -3 to -1. But then the shapes change. Well, the higher shape versus the lower shape changed. So now this graph is the higher, but now it becomes the line that was the lower. So there's 2 intervals for sure. So I would have going from -3 to -1, the 2x plus 6 minus the negative 2x plus 6. Not looking good already. Plus, now going from -1 to 5, I have the higher graph minus, and there's my brackets, the lower graph, and away you go. But you could do all that. Would it have been smarter to see if one graph was constantly more to the right of the other? It would have been smarter. Even though you would have to manipulate these formulas so that they were x equals y, this graph here, for any height, this value is always more to the right than the corresponding graph on the curved graph. So this is always more to the right for that whole interval. So I can set this up simply doing it one way. I would still have to write these in terms of x instead, still have to find where they meet, because now I want to know how high is this and how low is this. So you will be using radical graphs, and you have to remember in your solutions you'll be having to square radicals, and extraneous roots can appear. So you have to be observant when you're getting your answers and make sure they make sense. So taking these two equations, this one in terms of x would be y plus 1. So there's one of my functions. This one, moving my y's over and squaring everything, I will have 1/2 y squared minus 3. So it's still my same picture, absolutely. But now I would set these equal and find my meeting points. So if I set those equal and solve, algebraically I get 2. I get -2 and 4. So that now tells me that down here, the first place they're meeting is -2, and up here they're meeting at 4. So instead of looking sideways, I'm looking from here to here, and the integration, or the formula for area, is now one interval. So -2 to 4. The graph that was more to the right was this one, so I have x minus 1. Subtract this entire thing, and this entire thing was right here. x minus 1. Sorry, I'm supposed to be writing here in terms of y. So this is y plus 1 minusing this one. And this is all in terms of y. So you could, you'll multiply this, not multiply it out, you'll expand this, you'll put your constants together, and you will integrate, and it'll be way less work by hand versus what this one would have been over here. Okay, so I did, and I'm going to attach, and as part of Google Classroom, just showing you the work. So this will be on Google Classroom, that exact same question. What you're thinking was if you decided to integrate with respect to x, so basically leaving the equations the way they were, what would have been your thought process? I've skipped over a lot of math, but this is really, and undoing k values when you're integrating, and all sorts of things that you had to be on top of to get your answer, versus had you maybe changed the equations so that you're integrating with respect to y, same graph, and I didn't skip anything here. This was all the work that would have been left for me. But without that diagram, it's hard to make your correct decision, okay? And besides that, just one last thing. You can use your imagination. When you are given a certain region, how you may look at it might be smarter than anything any text has shown you. So you have the ability to add, to subtract, to use geometric shapes if you see them popping out at you to get that total area. So last question, if you were asked to find the area bounded by y equals root x, y equals x minus 2, and y equals 0. Well, those are pretty easy things to draw to see what on earth you're talking about. So we've got 3 functions. This is just the x-axis though. So I have a radical graph, and I have a linear graph going through -2, so I have something like this. So there's one of my region boundaries. Here's another region boundary, but here is the next region boundary. So this is what they're asking me for. So we're getting used to looking at these things horizontally versus vertically. For sure, if I'm going to look at this horizontally, there's my division right here. I would integrate saying my radical graph, all I'm really looking for is the area between that graph and the x-axis. So that's a basic integration from 0 to 2. But then from 2 to wherever these meet, which I believe is 4, so that was a bit more work seeing where these two meet. Now it's this graph minus the line. So that would be breaking it down into 2 intervals. How about if I look at this instead of kind of, which was the higher versus the lower, and looking at intervals sideways, how about if I look this way? Looking this way, I can see this graph is forever going to be to the right of this graph. So that might have been a better way of looking at this thing and setting it up. So depending how, if I left it like this and dealt with it like this, first of all, I would have to find where they meet, go through all this work, and I would have 2 regions. If I want to rewrite these, this one is then going to be x equals y squared. This one is going to be, let's see here. This is going to be x equals y plus 2. It still is the same graph, but now finding where they meet, I will have this vertical height right here given to me as 2. From the diagram, I can see my lower limit is 0. So this will be an integration then simply from 0 to 2. And it's the one that was more to the right. So that's my y plus 2, because I'm integrating with respect to y, minus the graph that was more to the left, which is my y squared. So this would not be too tough to do. So I would tackle it that way, probably being the better way. Other options though, you might have sat here and said, okay, since I've got all these different ways of figuring stuff out, how about if I just figure this or think about this entire area right now? How easy would that would be? It's a radical graph that went from 0 to 4. That would cover all of this orange area. But what do I want to take away? I want to take away a triangle, right? That's all this thing is. If it had a height of 2 and this distance is 2, then the formula for this triangle is base times height divided by 2. So I could, if I wanted, simply integrate this. Integrate the root of x from 0 to 4, and I will minus a 2 because that now gets rid of this piece, and maybe that would have been a faster way of looking at it in the first place. So lots and lots of options. So sky's the limit. So having a calculator, first step of anything I would do is try and get a graph of what I'm looking at. So I have the idea of upper, lower, or more to the right or more to the left, and therefore what would make more sense for me to tackle in terms of integration, integrating in terms of x or integrating in terms of y. So there are some questions in your textbook that they don't direct you whether you should integrate one way or the other. So that's when you're going to want to have a diagram. Otherwise, typically you go with the way they've given you the equation. If it's x equals, then you're probably going to integrate with respect to y and vice versa. Okay, so that's it. You might want to go back, read through some of this again, and then try the homework that's listed in your post in Google Classroom. Okay, take care.